Welcome back, everybody. In this lesson, we'll take a look at arc length, finding the length of a curve over a given interval, as well as surface area of rotation, right? If we take a region and rotate it, we've looked at how to find volumes. Now we'll talk about surface area, okay? But let's do arc length first, okay? So suppose we have some continuous function on the interval from A to B, and we're interested in how long that curve is, okay? How do we go about figuring that out, okay? Well, one thing we could do is we could basically take a couple of points and make a right triangle out of it, and then find the length of that hypotenuse to use as an approximation for the length of that curve over that segment, okay? And the idea is we could do a lot of these. We could find a lot of series of points, and we can make lots and lots of right triangles, and we could find the length of those hypotenuses to approximate the actual length of the curve, okay? And, you know, as we typically do in a course like this, we like to make things very, very small so as to get those approximations as good as possible. So the idea here is that we would take, you know, these 2 points and let them get as close as we possibly can together. And then that hypotenuse, I'll call it C, will be a very good approximation to the length of that portion of the curve, and then we just do a ton of these over and over and over again, and we add all those up to get our approximation, okay? So kind of like right in line with everything else we're doing with integrals, we're working with really small intervals, and we're summing them all up to get the total, in this case, length, okay? So let's talk about how we approximate, you know, using Pythagorean theorem. So again, I'll kind of blow this up a little bit. Here's our hypotenuse, which is going to approximate the length of the curve. Well, from left to right here, what that is a change in x. So I'm going to notate that with the delta x symbol. Up and down is some change in y, however much I went up and down. And again, I'm going to call the hypotenuse c. So using Pythagorean's theorem, we get c squared would be delta x squared plus delta y squared. And if I wanted to solve for the hypotenuse, what do? We take the square root of both sides. And again, what we're going to do is we're going to let delta x and delta y approach 0, so they get very small, and we get a very good approximation, okay? Now, I'm going to do a little bit of algebra on this, however, okay? What I'm actually going to do here to help clean this up a little bit is I'm actually going to factor out the delta x squared from underneath the radical. So it's going to look like this. It's still going to be under there. Okay? And then what would I need to distribute it into to get back to this? I need a 1 plus delta y over delta x squared. Okay, so try to see that. Probably can see if I distribute to the 1, that's going to give me that. If I distribute to the next term, okay, the delta x squares would cancel, leave me with the delta y squared that's in the numerator. Okay, and I'll just close that up there. And so we have this, all right, but now I can clean this up a little bit. We have the square root of a product. And that can be broken up into the product of the square roots. So let me just kind of come up here. All right, and now I can clean this up. What's the square root of delta x squared? That's just going to be delta x itself. Okay, and then there is an approximation to the hypotenuse over a very small change in x and y, okay? And so again, I'm going to rewrite it like this now. Okay, that would again give us one such hypotenuse over a very small interval, and if I want to sum up all of these, what do? We integrate, okay? So look, let me change the notation a little bit here. Instead of using delta y and delta x, let me write it like this, dy dx, okay? And now we're bringing back the notation that we're familiar with within the integral, and now the total length, we typically use the letter s for arc length, okay? It's going to be the integral of this thing from A to B, 1 plus dy over dx squared with respect to x. And there's our arc length formula, okay? Now dy dx is just our first derivative. So another way to write this formula is s equals the integral from a to b of radical 1 plus f prime of x squared dx. Okay, these are equivalent formulas, dy dx and f prime being the same thing here. Okay, so there's your arc length formula. All right, kind of a neat way that somebody figured out how to put that together. Most of the problems we're going to see will probably require the use of the calculator to actually punch them in and get the value. Again, with this stuff, I am much more interested in your ability to remember the formulas and set up the integrals, okay? Then you use something like Math 9 on your calculator to punch it in if need be, okay? If this was an AP exam problem, it would either be on the calculator portion. If it was on non-calculator portion, you'd be given functions that you could work with so that you could work this out by hand, okay? But in this lesson, again, the focus is going to be on setting up our integrals. And now we got our formula. So let's take a look. We got find the length of y equals x squared on the interval from 0 to 1, all right? So we all know what x squared looks like. For whatever reason, I'm interested in the portion of this curve. What is that length, okay? So, okay, arc length, we're going to say s equals, it's the integral from 0 to 1 of the square root of 1 plus f prime of x squared dx. So what do we need to do? We need to figure out what f prime is. Well, if f is x squared, then f prime of x is just going to be 2x here, okay? So our arc length, integral 0 to 1 of radical 1 plus quantity 2x squared dx, 0 to 1, radical 1 plus 4x squared. Okay, and this isn't something that we're going to work out by hand. If we were really interested, we could then punch this into our calculator or some other online platform and get its decimal value. Okay, let's take a look at the next one. Find the length of this weird-looking curve, x cubed over 6 plus 1 over 2x, on the interval from 1/2 to 2. So again, as soon as you know you're just finding the length of the curve, set up your formula. In this case, we'll have the integral from 1/2 to 2, radical 1 plus quantity f prime of x squared dx. Taking the first derivative, we're going to get 3x squared over 6. Let's see, this is 1 over 2x to the negative first, so we're going to get minus 1 over 2x to the negative second back. And so let's see, if we clean this up, we're looking at x squared over 2, or 1/2 x squared minus 1 over 2x squared. And that's what we're going to sub in for our derivative. All right, so arc length will be the integral from 1/2 to 2, radical 1 plus this whole thing squared. All right, folks, and that will give you your arc length. And if you're interested and you go through and punch that in, you should get, actually comes out pretty nice, 33 over 16 back. Okay, so if you want to do the practice of punching it in, you can do that. And if you need help, reach out to me. We can go through that together. Okay. And one more of these arc length problems, and then we'll take a look at surface area of revolutions. Find the length of the curve given by quantity y minus 1 cubed equals x squared on the interval from 0 to 8. Okay. So again, some strange sort of curve. I don't know exactly what this would look like with a y cubed and an x squared in it. But that doesn't matter. Here we're just practice setting up these formulas and seeing what we get. So here the distance will be the integral from 0 to 8 of the square root of 1 plus f prime of x quantity squared. Okay. So, you know, here we got to get f prime of x. So what we could do is try to get y all by itself. But that's going to be a little more on the tedious side. If I want to get dy dx, I'm just going to use implicit differentiation here, okay? So let's take a look at that. Using implicit differentiation, we're going to have 3y minus 1 squared times the derivative of the inside, which is our dy dx. On the right, we're just going to have 2x. And so dy dx is going to be 2x over 3 quantity y minus 1 squared. Okay, and there is our dy dx in this case. And let's see here. If we're going to integrate with respect to x, the only thing we got to be careful of is we do got to get rid of y here. Okay, so let's see if we can figure out a way to clean this up. So we got to figure out. I'm basically interested in looking at y minus 1 quantity squared. Can I find a way to clean that up using the original? Sure. So let's grab the original here. And basically what I want to know is what is y minus 1 quantity squared going to be in terms of x? Well, if I take the cube root of both sides, I'll get x to the 2/3 power. All right? And then if I square this, square, power to a power, you multiply, we're going to get that quantity y minus 1 squared is equal to x to the 4/3 in this problem. So coming back down here, dy dx, 2x over 3, and then I'm subbing that in, x to the 4/3. And now we can really clean this up. We got x to the 1st over x to the 4/3, and that's going to be what? X to the 1/3 in the denominator. Yep. And there we have it, okay? You can even go 2/3 x to the negative 1/3. And there's our f prime of x just in terms of x. So a little trickier here, and really the focus more on taking the derivative and getting it in terms of x than anything else, okay? And then from there, you're now just throwing it into this formula. And there you have it. And again, if you wanted to carefully punch that in, here you should get about 9.073. All right, so get the formula down, be careful taking your derivatives, watch out for implicit differentiation where that might show up, and put everything together, okay? Let me know if you have questions. All right, so moving on to surface area of rotation. There's the formula for it. Let's see where it comes from, okay? So coming back kind of up here, all right? Let me clean this up a little bit now. Get our function back in place here, okay? So we've got our function, right? And we're going to rotate it again. So we're back to rotations. For the concept, I'll rotate it about the x-axis here. Okay? And, you know, like I said, we've done volumes. This would end up giving us some disks here. But we're not interested in that now. Now we're interested in this overall surface area around the outside of this thing, okay? So how are we going to come up with that, all right? Well, the idea is this. Kind of think about what this region's made up of, right? If I take a small section of this, okay, this portion right here, and I were to revolve that, okay, basically I have this larger circle here and the smaller one a little behind it, I get this sort of a shape. And if I was to extend these lines, we basically get a cone shape. And so what we call this portion of a cone is a fulcrum. Okay, it's a portion of a cone, all right? And so what we can do is we can think of this region, again, as being made up of really an infinite number of these infinitesimally thin fulcrums, okay? And we're going to find the surface area of all these things and add them up, okay? So let's do some labeling here. I'm going to call this L. That's the length of the segment of the fulcrum, and that's going to approach 0 at the end of the day. Okay, we're going to have this larger radius in the middle. We'd have a smaller radius on the other side here. And it turns out the formula for the area of one of these is given by 2 pi RL, where R is the average of the two radii. Since we're going to let L approach 0 and get really, really thin and small, what's going to happen to the size of these radii? Well, they're going to approach each other. They're basically going to be the same value at the end of the day, and so we can just use R to represent that because it's going to be so small. These two values are going to be so close to each other that it's basically just the same value here, okay? So again, the trick with these formulas now is to figure out how do we get this in terms of X, okay? And here's the idea, all right? Says the overall surface area formula. I'll use A for surface area here, okay? Area is given as 2 pi integral a to b r of x times the square root of 1 plus quantity f prime of x squared dx, where r of x is the radius of the fulcrum in terms of x. So that's why I was going back up here when I say, look, the trick is to always get this stuff in terms of x. So r is going to represent the radius of the fulcrum in terms of x, okay? This is going to vary depending on which axis you're revolving around, okay? If we revolve around the x-axis, Okay, in blue here, the radius as a function of x is just f of x. If I have a region that I've revolved around the x-axis, this blue little radius here that I've labeled, right, I'm going up to the function. If this is my function and this is the x-axis, right, the length of that radius is just the function value. If, however, I revolve around the y-axis, now the circles are oriented this way. The radius now coming out to the right is given by whatever x value I'm at, okay? So the type of rotation matters here in that you're either going to use f of x to represent the radius or x by itself to represent the radius, and we're only going to be rotating these around x and y axes. We're not going to alter the lines of rotations for these. That gets kind of complicated and deep and is beyond what we need to be able to do, okay? In terms of this looks awfully familiar. That's the L portion of this formula, right? So we got the radius is either going to be x or f of x, depending. This L, again, is this length right here, and that's precisely what we talked about in the first part of this lesson, right? Was that portion, and we used, you know, we called that C before, but now I'm calling it the letter L. It's the same exact thing from before, which is why we get back exactly the same thing under the radical, right? It was just Pythagorean's theorem that we used to get that, all right? And so that's why these lessons are related. They both kind of use this idea here of approximating, you know, that hypotenuse, if you will, all right? So again, we got this formula. Let's take a look at a couple examples. We'll set them up on paper, and then if you want, you can punch them in, okay? So let's say we have x cubed on the interval 0, 1. We're going to rotate that around the x-axis and find the surface area. Something like this. Okay, and so look, the radius here is going up to the function. Okay, so the surface area is going to be 2 pi integral from 0 to 1, and now the radius function, r of x, is going up to the function. So here, our radius function is given by f of x, which is x cubed. So that's what's going in here for r of x times the square root of 1 plus f prime of x squared. F prime of x here is what? 3x squared. And there you have it. You could actually clean that up. You could use u substitution on it to get through it by hand if you really wanted to. But for now, you can punch it into your calculators as well. And you should get back, if you do that, about 3.563. Okay? So again, always good practice trying to punch that stuff in so you know if you can do it or not. And last but not least, we'll rotate the next one around the y-axis. The nice thing is it's still going to be all in terms of x. The only thing we got to account for is the radius here. So now we have x squared on 0 to radical 2. Rotate that about the y-axis, and this is the region we're dealing with here. So again, we get kind of like this, kind of like a soup bowl type of looking thing. All right, but now look, the radius is going from left to right. So here, the radius function is just given by x, okay? So look, area is going to be 2 pi integral 0 to radical 2. The radius is given by x, radical 1 plus f prime of x squared dx. F prime of x here is just 2x. And there's your setup. Again, if you wanted to clean this up a little bit, you could actually use u substitution to get through this. But if you're punching it in, you're going to get about 13.614. All right, so a relatively short lesson on these two concepts. Most important is know those formulas, how to apply them. And with the surface area stuff, you got to account for your radius. It's either f of x or just x based on the axis of rotation. As always, reach out with any questions, and have a good day.